My name is Jacob Bottomley, and this is Lab 3 for Physics 2212, Fields of a Magnetic Dipole. For this lab, we will experimentally observe the magnetic field of a permanent dipole magnet, and then compare those values to those predicted by a code using the Biot-Savart law for magnetic fields. The key concepts for this lab will be the Biot-Savart law, which is used to calculate the magnitude of the magnetic field at a given location, magnetic dipoles in the direction of the magnetic fields around them, superposition of magnetic fields, because we will need to take into account the magnetic field of the Earth, and distance dependence, how the strength of a magnetic field falls off as the distance between the source and the observation location increases. In order to measure the magnetic field of the bar magnet, we will be using the magnetometer chip found within my smartphone. We need to determine the exact location of this chip in order to get accurate distance measurements. In order to find the chip, we will align the bar magnet with one of the major axes of the phone, either the X or the Y axis, such that the component, the perpendicular component of the magnetic field created by the bar magnet will be 0. If we align the axis of the bar magnet with the y-axis of the phone, then we can slide the phone along the x-axis left or right until we find the point where the x component of the magnetic field contributed by the bar magnet is 0. If we mark this line down with a piece of tape, we can then rotate the phone 90 degrees and repeat the same process, except now sliding the phone along the y-axis with the bar magnet aligned with the phone's x-axis. Using this, we can find both the x and the y coordinates of the chip, and then mark the exact location on the phone. We know that the strength of the magnetic field created by the bar magnet will be given by the equation B equals k times r to the n power, where k is some constant, r is the distance between them, and n is some unknown power, and we want to solve for this value n. If we take the natural log of both sides, we find that it looks like a linear function with ln a natural log of the distance being the independent variable, the natural log of the magnetic field being the dependent variable, natural log of k being the y-intercept, and the power n being the slope. If we find the distance between the magnet and the magnetometer chip required in order to give a reading of a specific magnetic field strength value, then we can then gather the data required to create a linear regression graph that will give us the values of n and natural log of k. With the data from my experiments, we found that the y-intercept, natural log of k, is negative 14.1004, and that the slope, or the power, of r is n equals negative 2.89. So far, all of our measurements have had the phone magnetometer chip placed directly along the axis of the bar magnet. However, we also want to measure at a point not along this axis. We'll place it at a point at a 45-degree angle from the axis of the phone, and then compare this to a value predicted by our code. We can only align one axis of the phone with the magnetic field of the Earth in order to cancel out the components of the magnetic field contributed by the Earth, so we'll need to keep track of the other one so that we can subtract it from the overall magnetic field measured by the phone to calculate the magnetic field contributed only by the magnet. Our code will simulate the magnet by creating a dipole using the measurements gathered from the code. In order to calculate the magnetic field at given points around the magnet, it will be using the following equation shown on screen to calculate the magnetic field. The value from our experiment that we need to input into the code is mu, which is the magnitude of the magnetic dipole moment. We can calculate this using a simplified version of the Biot-Savart law when the relative position vector is parallel to the axis of the dipole. Solving this and then using our graph, we can separate the k constant value into mu naught over 4 pi and then times 2, and then our dipole moment mu, and then solving for using our values that we found with our linear regression, we can solve for a value of mu being 3.747. In our code, we have this initial function, dipole b, that takes the input of our value mu, and then r, which will be a relative position vector between the observation location and the magnet in order to calculate the magnetic field. Then in the code shown below, we find the magnetic field at 2 points along the axis on either side of the magnet, equidistant from each other, and then create an arrow to represent them. And then we do the same at end up being at 12 other points, 4 on the parallel axes, or perpendicular axes to the magnet axis, and then at 8 points on corners at a 45-degree angle from the magnet. This image is the graphic created by the code. The white low bar in the middle is the magnet. The orange arrows represent the magnetic field along the axis of the magnet. The blue ones are the magnetic field of points on the perpendicular axes of the graph, and then the magenta arrows are the fields at points at a 45-degree angle to the axis of the magnet. So in conclusion, our lab for distance dependence, our results are fairly accurate. The calculated value of n was negative 2.9. In reality, the value is 3, so they're very close because it's the strength of the field is proportional to 1 over r cubed. Our experimental value of the magnetic field at a 45-degree angle God damn it. Fuck. The experimental results for the magnetic field at a 45-degree angle from the axis of the magnet were also very similar to those calculated by the code. The ones calculated by the code were 3.4 times 10 to the negative 5th Teslas, and the experimental was just under 5 times 10 to the negative 5th Teslas. So those are well within an order of magnitude of each other, and so are very accurate. Throughout this lab, we try to align the phone with one of the axes of the phone with that of the magnetic field of the Earth. This is in order to cancel out one of the magnetic field components of the Earth. If we did not do so and had it at some other angle, our results would be different because there would be extra components of magnetic field being contributed. However, if we took the baseline values without the external magnet, we took that value into account, we could subtract the initial values of the Earth and still get the same results.